Since we've talked a lot about electrostatics and electricity, we're going to move now to magnetism, which is connected to electricity, but it'll take us a little while to get to the full connection. First, we're going to start with what you know or have some experience of, and that is with north and south poles. So we look at a magnet, like a bar magnet, where we label a north pole and a south pole, and then we can think about what happens when we bring a compass up next to this. So if we bring a compass, then what happens is that we get a little arrow like this. This is the north and south, right? Because opposites attract. It's just like the electrical case. So in fact, any north pole of a compass, I'm going to stop drawing the circles around it, are going to point like this. Right? That's the way the compass is going to point, which means that we're going to be repelled in this direction. It's going to be repelled here, attracted here, and as you get closer in, it's obviously stronger, and as you get further away, it's weaker, and so we get magnetic field lines like electric field lines that look something like this. They sort of go out and come on like that, so they're coming in, they're going away from the North Pole, coming towards the South Pole. So these are magnetic field lines. And our magnetic field is not represented with an M. We already have that for mass. And so it actually turns out that we describe that with a B. I don't know why. So the magnetic field lines, the direction and the strength, we describe it with a vector B. And you can see that here, right, this is supposed to be symmetric. So we kind of go like this. All right. So you can think about taking your compass, and if you lined it up here, it would point sort of in this direction. Now my initial compass is not so good, so let's put it right along a field line like that. So that's the way you can think of little tiny little tiny compasses that are our detectors. Just like we had a test charge, we sort of have a test magnet here. The thing to notice that's different, one of the things that's different about magnetism, is that we always have a north pole with the south pole. So they're always paired. So we have a north and a south, even if we break this. So if we break this into pieces, what happens is we get a south and a north right in there, and we get two magnets. Okay? So it doesn't matter how small we break these down. We have never seen an individual, what's called magnetic monopole, a north pole without a south pole. And that has to do with how these are created, because they're actually created from moving charges, from currents. And so once you see how they're created, you can see how we get, how we can't have one without the other, at least in our picture of these. Something to point out is that if we look at the Earth, right, and this is the Arctic, where Santa Claus lives, Santa's home, up here, and then we have Antarctica down here. Then when we take our compass, notice that our compass points this way. That's north and south, north and south. So we can think of inside the Earth as there being a big pole, right? It's actually not a big magnet. It's moving charges that do it. But notice that what we call our geographic North Pole, so where Santa lives, is our geographic north, because it's the northern hemisphere. But notice it's really a magnetic South Pole. So you see, your parents lied to you if they told you Santa lived at the North Pole. Santa lives at the South Pole. Well, the South Magnetic Pole. Okay, so, and then we could draw the same field lines, which we can detect right here. Okay. And then they kind of go out like that. And they have some useful effects, right? But they have flipped. The magnetic north and magnetic south over geologic time have flipped, and we know that because of magnetic flow of hot magnetic rock lining up with the poles at certain times in the Earth's history. So we have sort of a map of what the magnetic field looks like and how it flips over time. Okay, so this is sort of our description. So what we know is that north points to south, south ends of magnets point towards each other, and so north poles repel each other. So if I took two north poles and put them together, for example, I took two magnets like this, so I put a north and a south, and then I bring a second magnet, a north and a north. You know, trying to bring these together is really hard. What happens is the magnetic fields sort of really diverge from each other, if you like. Okay, and then they're going to curl back. They're not so uniform at that point. These are really diverging from each other. And then, sorry, over here they look really diverge, and then they kind of come back to being more normal on the other side. So when we have two north poles together. But if we have a south pole and a north pole, and then a south pole and a north pole, two magnets like that, they're attracted to each other. But if they're held in place, then we can draw the magnetic field is nice and strong. That's the direction of our B field, our magnetic field. And so we're going to talk about first not the magnetic forces between permanent magnets, but the magnetic forces on charged particles. Okay, so the magnetic forces on charged particles. And this is why I had you review the cross product, because it's in terms of the cross product. So the magnetic force is equal to charge times how fast the charge is going across the direction of the magnetic field. So for example, if we have a magnetic field that points in this direction, and we'll talk about how we generate such things, it's sort of like this setup. So we have a magnetic field that's just going in that direction. If we have a positive charge, so I have a plus charge, and it's just sitting there, it does not experience a force. It must be moving. And notice that if I send this way, right, the cross product, if you remember, F magnetic, the cross product is Q times V, the magnitude of it is Q times V, then times the sine of the angle between these two vectors. That's the magnitude of the cross product. So in this case, the angle between them is equal to 0 degrees, so the magnetic force is equal to 0. So they need to not be in the same direction. Okay? So if we set up our magnetic field like this, and we have our charged particle going like this, here's our V, here's our B. If we come down here and use this right-hand rule, okay, so if you remember, this is your first finger is your, has to be your right hand, right? So right hand. And your first finger is along the first part, so we're doing F, let's see, F is equal to Q, V cross B. So that means we put the V along our index finger and our B along our middle finger there. So we can go V would be up, B, at least for me when I'm looking at this on the screen, I kind of have to rotate my hand, and then we can find out the direction of the force. So it may be easier to draw it up here so you can kind of see the two vectors together. So V and B, V cross B, gives me something that is into the page. So that would be the direction of the force. The positive charge would feel a force into the page. This gets three-dimensional very, very quickly. Okay, so we're going to use a little toy model here where we've got a north pole, which is the red side is the north, and the blue side is the south. So my magnetic field points from north to south, so you can see the arrow there for that. And so what I'm going to do is say, let's imagine we have a charge moving in some direction. So if we have, for example, a charge that's moving up, so that would be, I'm going to take my right hand, so I've got my right hand here. So my charge is up, and my magnetic field is along my middle finger, so here, so up and middle finger, then my force is coming out from this page. Okay, that would be the direction of the force. If I say my charge is going into the page, so that's the direction it's going, this is a more natural way for me to do this lined up. So my charge in my index finger, that's the direction of V. My magnetic field is that way, and then that gets me then a force that's up. Okay, so if we look at this, we have a magnetic field that goes in this direction. So there's my magnetic field going from north to south. That's the direction the compass would go. And if we have a V that's coming out of the page, then my V cross B gives me a force that is then down. When I do my right hand rule, that's what I get with that setup. And then you can check the other ones as we go along. Now very quickly we see that this gets to be a little messy to draw these three-dimensional diagrams. So we develop a convention, and that is that, that when we're looking at a vector, particularly a magnetic field, we can describe it as going into the page as saying that would be a bunch of X's, would be into the page. Okay, think of it as the back end of an arrow, right? So an arrow looks like this, and often it has the fletching back here. I think that's what it's called, right? And so as that arrow is leaving you, you see this X. So that's into the page. And then out of the page, or out of the screen, I guess I should say in this case, we have dots, right? Because that would be what sort of the tip of the arrow coming at you, which maybe you don't want to see an arrow coming at you, but that is the dot of the arrow coming towards you. So that's our convention to draw often the magnetic field. So we don't have to have quite so many three-dimensional things. So if we have that, we can look at a situation, say, of a magnetic field that is into the page, and we have a charge that's traveling along like this. Okay, so now our V is traveling to the right. That's our first finger. And then our second finger is into the page. That's a little easier to do. Notice that that gives you, here, if we put this sort of in here, this V, so our V is that way, V cross B, that gives us a force that is up like that. And so in fact, if we have something that is into the page like that, excuse me, and a particle comes in to a magnetic field like this, and it's a constant magnetic field, just one value, some number of Tesla. So the units of magnetic field, I guess I should have said this earlier, is a Tesla. If we have a constant like 1 or 2 Tesla, then what happens is that force causes this to start to bend. Okay, so that's the path this starts to go on. And as soon as that bends, right, then its velocity is in that direction. Velocity in that direction, magnetic field into the page. That gives us a force like this. And what we see is that we keep bending it around. Oh, that's really terrible. Let's try that again. It keeps bending around and round, and this force is always perpendicular because it's a cross product, it's always perpendicular to the velocity. So there's the velocity, there's the velocity, and so it makes a circle. So you can get charged particles. So we're going to send a V this way. This time the charged particles will go like this. Ooh, it's not a great circle. A semicircle until it comes back out. There. And you can actually, just by using centripetal acceleration, we can actually find the radius of the circle. Right? So we can say, in fact, the force that acts on this charged particle is going to be mass times the acceleration, and the acceleration is going to be that centripetal acceleration. So A acceleration is equal to V squared over R. And then the magnitude of the force is Q V times B times the sine of the angle between them. In this case, because the velocity is in this direction and the magnetic field is out of the screen, or in the right, or the X is into the screen, and either way this is 90 degrees, and it doesn't change as this curves around, it still stays 90 degrees. So sine of 90 degrees gives us a 1. So if we put that in there, that gives us the magnitude. Then that tells us QVB is equal to, so I put this on this side, and then the right-hand side becomes mv squared over r, or I can solve for r, right? One of these v's goes away, and r is equal to m over q v over b, if you like, or mv over qb. And so you can get solutions for how big a circle, right? If you're going faster, if v is bigger, then your radius is going to be bigger because your magnetic field doesn't bend it in as quickly, okay? It doesn't make a really tight circle. Similarly, if your magnetic field gets bigger, right? If that increases, then that's in the denominator down here, which makes this smaller, which makes a tighter circle. So the force forces it into a tighter and tighter circle. So you can get some information that way. One of the really good things this allows us to do is actually find the charge over mass ratio for particles. So this is a way that we separate particles by mass, and it's the basis of a lot of mass spectrum.